Hi guys, it's Mrs. Jackson. In today's video, I'm going to show you how to make calculations of pH for buffering solutions. I know that you have taken notes over what a buffering solution is, so we'll do a quick review of buffer solutions. We're also going to do a quick review of calculating the pH of a weak acid or a weak base. So have your periodic tables. I would recommend having your data booklet out, and I would have my calculator and notes out. Earlier, you have learned that a buffering solution is a solution that resists changes in pH when you add small amounts of a strong acid or small amounts of a strong base to that solution. And the reason that a buffering solution can do that actually goes back to what a buffer is actually made of. There are two types of solutions that we're going to look at. We're going to look at acidic buffering solutions, and we're going to look at basic buffering solutions. A buffering solution will have either, like in this case, a weak acid and its conjugate base, or, as we will see in a little bit, it can have a weak base and its conjugate acid. In this image, what you are looking at is a representation of molecules of acetic acid in green and the acetate or ethanoate ion in purple. And a buffering solution, how this is going to be different from the weak acid, weak base calculations that you've done previously with ice charts, is that in previous calculations, we've started with our ice charts like this, and we've had maybe a concentration of our weak acid, and we started off with 0 here and 0 here. The way that buffering solutions are going to be different is instead of starting off with 0 in your conjugate base, or later on with the basic buffers conjugate acids, is you will have some quantity here. The ideal buffer has the same concentration of your weak species and its conjugate, but those aren't the only kind of buffers there are. They can come in different concentrations, but the ideal buffer with the highest buffering capacity will have equal molar concentrations of both the weak species and its conjugate. So when we start talking about forming a buffer, formation of a buffer can take place in a couple of ways. I'm going to start with just the simplest form, and then as we get into titrations, we're going to start talking about the second way that buffering solutions can be formed. The easiest way to form a buffering solution is what you see illustrated in these pictures here. You take a solution of for example, in the picture on the left, a weak acid, and you pour that solution into a container, and then you have another solution that has a salt with a common ion. So if you look at the illustration on the left-hand side, we have acetic acid, which is the acetate ion with the hydrogen. We've worked with that as ethanoic acid as well. That is one solution that we see on the left. And on the right, we're adding a solution of a salt. Okay, sodium acetate is a salt, NaC2H3O2. When we dissociate that in water, the sodium completely separates from that acetate ion, and you wind up with only the acetate ion in solution doing anything of any interest. So when we go back and we look at this example here, the acetic acid or the ethanoic acid would be in one solution, and then you would have this anion from that salt in the other flask. So that's what we're doing here, is we are taking the acetic acid solution on the left, we are adding a solution of sodium acetate, and what we wind up with, you can see down here at the bottom, is we have a solution of acetate ions, and in that same solution, we've got that acetic acid as well. So that's how we can form a solution, or that's one of the methods we can use to form a solution. Over here on the right-hand side, in the image on the right, is the same idea, same concept, but with a weak base instead. So you can see here that in this flask, we've got our weak base ammonia, and in this flask, we are adding a solution of ammonium chloride. So when we are talking about ammonia and ammonium, we've got ammonia NH3 that interacts with water, reaches the equilibrium, and we wind up with ammonium NH4, and I'm going to squeeze it in, hydroxide. So when we take this flask that we have right here on the right-hand side, that ammonium chloride solution adds the ammonium ion. The ammonia comes from the weak base solution, and then we add the ammonium, NH4, directly from this flask. That's how you can easily form a buffering solution. Again, when we start talking about it, we're really talking about something that starts with both the acid and its conjugate base, or alternatively, the weak base and its conjugate acid. All right. Now that we've talked a little bit about what acids and bases are, or what a buffer solution is, now it's time to do a little bit of review. So let's take a look at some calculations. For our first calculation, we are going to be simply calculating the pH of an unbuffered 0.01 molar acetic acid solution. So here on the left, I've got the Ka expression written. Remember, it's always products over reactants. So the products in this dissociation are the acetate or the ethanoate ion here, okay, the hydronium ion, or in our case, we usually use hydrogen ions, and that is over the concentration of the weak acid. So in our case, this acetic acid. Now the Ka value for this is given in the problem as 1.8 times 10 to the negative fifth. In your data booklet, you are given the pKa values. So do remember that if you are trying to go from pKa to the Ka value, your Ka value is going to be 10 to the power of negative pKa. So if you have a pKa value of 4.74, 10 to the power of negative 4.74 is this 1.8 times 10 to the negative fifth. So you should be able to make those conversions without any difficulty. So as we get into our calculation and we're wanting to calculate the pH of our unbuffered solution, keep in mind that when we start, we have a given concentration of 0.01 molar acetic acid solution. And I don't have any hydrogen ion or any hydronium ion, and I have no acetate ion in my equation. I don't have any present in my solution, so those are each going to start at 0. So we should remember from equilibrium that this reaction is going to have to go forward because it's going to have to fill in both of those zeros. So as I move my reaction into the forward direction, I'm going to lose ethanoic acid, and I'm going to form hydrogen ions. And so when we move forward, we are going to decrease the amount of our ethanoic acid by some amount X. And as I move forward, I'm going to increase the amount of hydrogen ions and the ethanoate ion or the acetate ion as I move forward. So keep in mind, we started off only with the acetic acid in solution, and so that forced my reaction to move forward to fill in the 0 here and the 0 here. I know that these are all X value because I have a 1 molecule, okay, or for every 1 mole of the acetic acid, I will produce 1 mole of hydronium or hydrogen ions, and I will form 1 mole of acetate or ethanoate ions. That's why all of those are X. After my system reaches equilibrium, remember this is going to reach an equilibrium where the forward and reverse reactions are happening at the same rate, I'm going to have my original concentration, 0.01, but I'm going to subtract the amount of the acid that moved forward to reach equilibrium. So at equilibrium, I have 0.01 minus X. On the other side, I have X amount of the hydrogen ion, and I have X amount of my ethanoate or acetate ion. Now, do remember that we have learned that X is negligible. So when we are asked for an assumption that we can make about this calculation, we say that X is negligible. And remember, that means by comparison to the original concentration of 0.01, the amount of X is actually so small that if I subtracted it from the 0.01, the resulting number would still round to 0.01. So we say that X is negligible. To solve then for the value of x, we put all of our equilibrium values into the equilibrium expression here. So when I solve for my x value, I've got my Ka value of 1.8 times 10 to the negative fifth is equal to, I'm going to have x squared on top because I've got x amount of hydrogen going here, and I've got x amount of the ethanoate ion going here. X times x is x squared. And then I have that over the original concentration of my ethanoic acid, which is the 0.01 value. So 0.01. When I solve that, my x value is going to be 4.24 times 10 to the negative fourth. And that, remember folks, is the hydrogen ion concentration. The pH of that is the negative log of 4.24 times 10 to the negative fourth. You should calculate a pH value of 3.37 for this initial calculation. That's all review. We've done those before, and you were very proficient, very good at those. Now let's look at how things change if we have a buffered solution. So this is the new stuff. So be sure you pause, go back over the review if you need it, and then jump forward for the new stuff. Now we're going to calculate the pH of a buffered 0.01 solution. What we're going to do when this equation or this problem is worded a little bit funny, it is a buffered solution. We're going to understand that that means it is the ideal buffer, which means I have 0.01 concentration of the acetic acid and of the ethanoate ion. So when I start my ice chart, it's going to look very similar to the other ice charts we've done. I'm going to start with 0.01 molar concentration of my ethanoic acid. I don't have any hydrogen, but I'm starting with a value for my conjugate base, or this ethanoate ion. And that value in this particular problem is going to be 0.01 molar as well. So you can see that this is looking different in one very important way from the last problem we worked, and that is the fact that I'm beginning with something on the right-hand side. But I still have a 0 here for my hydrogen ions. So equilibrium principles say it has to move forward to fill in that 0. So when we start making our ice chart, I'm still going to go down by some amount x because I have to go forward to fill in this hole for the hydronium or hydrogen ion. So this side is going to increase by x on both of those. So then at equilibrium, when I get to equilibrium, I'm going to have 0.01 minus x. I'm going to have x amount of the hydrogen ion, and I'm going to have 0.01 plus x. But just like we did on the last example, we are going to assume that the x is negligible in both cases. We're going to assume that that value of x, even though it's got a starting quantity on the right-hand side, that x amount is still going to be so small by comparison to the 0.01, we're going to ignore it. So when we put that into the same Ka expression, so my Ka value is still 1.8 times 10 to the negative fifth. I am now going to substitute in these values on this equilibrium line for my K expression. So I have X amount of hydrogen. I've got 0.01 of my ethanoate ion. And I have 0.01 of my original acetic acid, and that goes down here. So 0.01. Okay. In this case, my X equals 1.8 times 10 to the negative fifth. If I take the negative log of that for the pH, my pH is going to be 4.74. So you can see that the pH for this solution is a little higher than it was with my first solution. The first solution had a 0 for ethanoate ion, and it calculated to have a pH of 3.37. Now, with my buffered solution, I have a quantity of the ethanoate already in my solution, which prevents this equilibrium from going all the way forward. So it actually made the amount of hydrogen ion smaller because I already had some ions in solution, and that prevented the full dissociation moving forward. Now I have a higher pH because I had fewer hydrogens come forward. So that's the basic gist of calculating a buffered solution. The big thing that you need to walk away with today is that a buffered solution begins with a quantity of your weak species, in this case our weak acid, ethanoic acid, and a quantity or a concentration of the conjugate base, in this case the ethanoate. For our next calculation, we're going to look at a basic buffer instead of an acidic buffer, but these are going to calculate the same, but one of the key differences is you have to keep in mind as you're calculating that you're working with hydroxide ions. So this is that weak base that I showed you being prepared on the second or third slide. I have a quantity of the ammonia, and I have a concentration of the ammonium as well. And again, this could have been formed a couple of ways, but we're just going to assume that a solution of ammonia and a solution of ammonium chloride were added together to form our buffering solution. So in this problem, we're finding the pH of our solution, and I have 1 mole of ammonia and 0.4 moles of ammonium chloride, and they're mixed to give a liter of solution. Now, technically, when you work your calculations for the ice chart or when you're working with pH, your concentrations or your values have to be in concentration, which is always, remember, moles per liter. This one is nice and easy because this is in 1 liter of solution. So when I go to make my ice chart, it's a pretty easy calculation to make. So here's my ice chart. Remember again, I'm starting with 1 mole in 1 liter. So I'm starting with 1 molar solution of the ammonia. I don't worry about water. And I've got 0.4 moles of ammonium. Remember the chloride, those spectator ions are not really going to do anything, so we just ignore those. But I am starting with 0.4 moles of ammonium in that same liter. So I have 0.4 molar ammonium, and I am not starting with any hydroxide in solution. Remember that ammonia is a Bronsted-Lowry base. It took the hydrogen from water. When ammonia takes the hydrogen from water, it becomes ammonium, and that leaves the hydroxide ion behind. When we look at our next line in our ice chart, because I have a 0 in my equation, I know that equilibrium is going to pull this forward. Remember, I have to move forward to fill in any holes, and that's what I have. So I know that the ammonia concentration will go down. I know that the ammonium concentration is going to go up, and I know that the ammonia or the hydroxide concentration will also increase. So when I reach equilibrium, I have 1.0 plus or minus x. I have 0.4 plus x, and then I have x amount of hydroxides. As we did before, we know that the x is negligible. Okay. And so I ignore the x's that are being added and subtracted. And I'm going to put these into my KB expression. So you can see up here at the top, we are given our KB value For ammonia, 1.8 times 10 to the negative fifth. My Kb expression looks like this. So Kb is equal to concentration of the ammonium, NH4, times the concentration of hydroxide, OH minus, over the original concentration of the ammonia, NH3. So when I substitute values in, I have 1.8 times 10 to the negative fifth is equal to, and I'm going to substitute in my value. I've got a 0.4 times x over 1.0. So when I solve for x, my value of x in this case is 4.5 times 10 to the negative fifth. And when I take the negative log of that, I find that my pH, or I'm sorry, POH, okay, is 4.35. To find the pH, I take 14 minus my POH and my pH value, and I'll write it separately in a different color because it's getting crowded. The actual pH value for this one is going to be 9.65. And we always want to give it the smell test. Does 9.65 seem right? Does that smell like it could be a good answer? It does, because I'm working with a basic solution. Okay, so that is making some general calculations for buffering solutions. But there's got to be an easier way, and there is. The ice chart will always work, but we have an easy button. And the easy button, if you learn to use it, can save you a lot of time. You just have to remember it only actually is going to work if we're working with buffering solutions. The easy button is called the Henderson-Hasselbalch equation. And we have one for weak acid solutions, and you can see the pH, and we have one for weak base solutions, and you can see the POH. This is a super simple equation to use, and it's really nice to use for the IB test because you are using the pKa, and that is given directly in the data booklet. Also, the Henderson-Hasselbalch equation, if I'm not mistaken, this equation, I believe, is also given in the data booklet. If you know how to use it, a tremendous time saver. So let's look at this problem that we just solved, but instead of working through the ice chart, let's use the Henderson-Hasselbalch equation. So I'm going to fill in my values for the Henderson-Hasselbalch equation here. I'm just going to fill in my values from my problem. So let's get those sketched in really quickly. My concentration of the ammonium here, the ammonium is 0.4 molar concentration. The concentration of the ammonia, remember, was the 1 mole divided by the liter, so it's 1 molar concentration. So when I plug that into my POH equation, or the Henderson-Hasselbalch, my POH is equal to the pKb. So to get my pKb is the negative log of Kb. In your data booklet, it is given as 4.74. So I've got 4.74 plus the log of the concentration of my anion, or my cation, ammonium, 0.4, over the concentration of my ammonia, 1.0. When I plug that into my calculator, my POH comes out to be 4.35. When I take 14 minus 4.35, I wind up with the 9.65 pH. Just like we had on the last problem, it's just a tremendous time saver. So definitely recommend that you learn how to use the Henderson-Hasselbalch. It will save you a lot of time. It will only work for buffering solutions. So now let's try another problem with a weak acid. Okay. In this case, you can see that it's just a very generic weak acid. Remember, we said early on that the H is the hydrogen, the acidic hydrogen, the A is our anion. So this is my weak acid on the left. This is my conjugate base on the right. In this particular calculation, I know my concentration of the weak acid initially is 0.02. So I've got a 0.02 molar concentration of my weak acid, and I see that I have a 0.01 molar concentration of my weak base. In this particular problem, you are given the pKa just like you would be given in your data booklet, so you're really ready to start filling in the values that you know into Henderson-Hasselbalch. So my pH of this buffering solution is going to be the pKb of 5.0 plus the log of my anion concentration, 0.01, divided by my weak acid concentration, 0.02. When I calculate that value, the pH of this solution is going to be 4.69, and that would be my final answer. Again, it's a mighty big time saver over doing the ice chart, but it only works for buffered solutions because you have to have that initial concentration of the conjugate species. Let's do a couple more examples. So this is an example using a 50 milliliter sample of my buffering solution. I've got 2 molar concentration of my acetic acid, and I have a 2 molar concentration of my sodium acetate. So when I begin, I know that my acetic acid concentration is 2.0 molar, and I know that the anion concentration is also 2.0 molar. So when I put that into Henderson-Hasselbalch, pH is equal to my pKa of 4.74. That's in your data booklet, plus the log of 2.0 divided by 2.0. Well, 2.0 divided by 2.0 is 1, and the log of 1 is 0. So in this case, my pH is equal to 4.74. If you come into a circumstance like this, where you have in your buffering solution, when you have in your buffering solution equal concentrations of your weak acid and of the conjugate base ion, okay, you're at a very special point in your reaction when you have equal amounts of the weak acid and its conjugate base. Okay, the pH will equal the pKa. Okay. It's actually referred to, and we'll explain why as we get into our titrations. This is actually called the half equivalence. This is at half the equivalence point. You might jot that down in your notes. As we get into titrations and we talk about this, that 1/2 equivalence is going to be very important. At 1/2 the equivalence point in a titration, remember, the equivalence point is where the moles of the acid and the moles of your base in the titration are equal. If you are at half your equivalence point, you have neutralized half of your acid. We will come back to that again as we go through titration calculations, but I want to point it out now so that it's not a new term when we get to it. But at 1/2 equivalence, pH equals the pKa. So, well, what does a buffer do? Okay, well, buffers, we said early, will resist changes of pH when you add a strong acid or a strong base added to them. The reason they can do that is because buffers contain both a weak acid and a conjugate base. So no matter what I add, I've got something that will react with it. Remember that acids and bases react. So if I add an acid, it will react with the base, the conjugate base. If I add a base, it's going to react with the conjugate acid. And that's what we see illustrated here. If I am adding hydrogen to my solution, that hydrogen ion that I am adding is going to react with the anions in solution to form more of my weak acid. If I add hydroxide to my solution, that hydroxide is going to react with the weak acid of my buffer to form more of the anion and more water. All right, so what does this look like in practice? Right, so here is our ion or our buffering solution we've been working with. So I've got my weak acid on the left, I've got my strong conjugate base on the right. If I am going to add hydroxide, hydroxide will react with my acid. Okay? So when I add the hydroxide to my solution, it reacts with the hydrogen of my acid to produce water and more of the anion. Okay. If I add acid to my solution, it's going to react with the anion to produce more of the acetic acid. So you just have to stop, think, what do I add? What do I have? If I'm adding an acid, it reacts with the conjugate base. If I'm adding the base, it reacts with the acid. We're going to do some examples. All right, so this is the same equation that we worked with earlier, but it is moving forward with this concept. So now I am going to take 2 milliliters of a hydrochloric acid solution and I'm going to add it to the buffering solution that we just worked with. Okay, so the couple of things you need to be aware of. Because I'm going to have a reaction, okay, I'm going to have a reaction between hydrochloric acid and my conjugate base. Because this is an acid, it will react with the conjugate base. Because it's a reaction, I need an equation. So the first thing I'm going to do is write that equation. My hydrochloric acid, HCl, is going to react with my conjugate base, or the ethanoate ion, CH3COO-, pulled it just from the equation. When they react, the hydrogen from this hydrochloric acid, remember hydrochloric acid is a strong acid, so it completely dissociates. That acid will release all its hydrogen, and that hydrogen will be attracted to this negative ion. When it forms the new acid, we wind up with CH3COOH. Remember that was the weak acid we started with, and chloride ions. But because chloride ions have come from a strong acid, they are spectators, and we ignore those in our equation. So this is a chemical reaction between this hydrogen from the strong acid and the anion of my buffering solution. Remember that the weak acid in the equilibrium expression is favored, and so that hydrogen will be attracted to that acetate ion to reform the acid. But what that means is I've just changed the concentration of acid in my buffering solution, which is going to have an impact on the pH. So we need to figure out how much of that has happened. So because this is an equation, we must have moles, right? We're doing a chemical reaction equation, and when we do stoichiometry, we must have our values in moles. So for this, we're going to go back to our old friend, molarity is equal to moles over liters. All right. So I have 2 milliliters of 6 molar hydrochloric acid. So when I plug in 6 molar is equal to X number of moles over, remember to convert that to liters, 0.002 liters, I wind up with 0.012 moles of my hydrochloric acid. So I'm going to plug those in really quickly. 0.012 moles. I'm going to erase some of this so that we've got a little bit of room to do some work. And we are going to write what's called a bra chart. When we're doing this chemical reaction, we need a different kind of chart to keep track of what we're doing. So we are looking at the moles before, the moles that react, and the moles of everything that we have after. And that's where it gets the name the bra chart. So now I've got the moles of my hydrochloric acid, and I need to now determine how many moles of the acetate ion I have and how many moles of the acetic acid I have. Because I have both the anion and the acid in solution, I want the moles of each of those. So when I come up to the top and I look, I have 2 molar concentration of each of my parts of my buffer. I have 2 molar concentration of the acid, and I have a 2 molar concentration of the acetate ion. Remember that we are ignoring the sodium. It's just a spectator like the chlorine. So when I calculate the number of moles for my acetic acid and for the acetate ion, I'm going to use the same molarity equation. Molarity is still moles over liters. They are both 2 molar in their concentration, so I can do both these calculations at once. So 2 is equal to X number of moles over, and I have a solution that has a 50 milliliter volume. So converted to liters, that's 0.05, and that means that the moles for this are going to be 0.1 molar, or moles. So I'm going to put that in to my before line. So 0.10 moles, and I have 0.1 moles of the acid. And now I'm ready to react. So I'm going to get some room so we can continue calculating here. So what happens next is these are going to react, and this is where you have to remember your stoichiometry. These are all reacting with a 1:1:1 ratio, but I have significantly less of the hydrochloric acid. So this hydrochloric acid is going to be my limiting reactant, and so that's going to be entirely used up. So I am going to use up all 0.012 moles of my hydrochloric acid, and as I use that up, I'm also going to use up an equal amount of my acetate ion. And now this is moving forward, right? So this is going to be moving forward, so I'm going to be forming the same amount of the acid, 0.012 moles. So when my reaction is over, after everything reacts, I have 0 hydrochloric acid left. Okay, I have 0.1 minus 0.012 is 0.088 moles of the acetate ion left, and I have now formed 0.112 moles of my acid. And I'm going to need to go forward and put this back into Henderson-Hasselbalch. Okay, but to do that, I need concentrations. These are moles, so to get to concentration, again, remember the molar equation, molarity is moles over liters. I have 0.088 moles, and I have a new volume. I have my 50 milliliters that I began with, and I added 2 additional milliliters. And so I have a total now of 52 mils, which is 0.052 liters. When I divide that out, I get a new molarity of 1.69. I'm going to do the same here. I'm going to divide it by the same 0.052, and that gives me a new molarity of 2.15. And that should make sense if you think about it. I added an acid to my solution. My acid reacted with the base to form more acid. So I should have a higher molarity, oh dear, of my acid. I should have a higher molarity of my acid because I created more acid. So now I have two new concentrations. I have a 0.169 molar acetate concentration and a 2.15 molar acetic acid concentration. So when we come back over here and we're ready to use Henderson-Hasselbalch, pull this up from the bottom for us. I'm ready to use Henderson-Hasselbalch again. When I go back to my slide and I look at how much of each I had, I've got a 1.69 molar concentration of my conjugate base, and I have a 2.15 molar concentration of my acid. Keep in mind that we're using this equation here. So when I come to my new slide, okay, my concentration of my acid is 2.15 molar, and the concentration of my conjugate base is 1.69 molar. So I can plug those into my Henderson-Hasselbalch equation. So the pH of my solution is going to be the pKa of acetic acid, which is 4.74. That's in your data booklet, plus the log of my anion, 1.69, over the concentration of my acid, 2.15. So my pH of my new solution is going to be 4.64. So my pH, okay, did drop just a little bit, but that makes an entire, it makes sense entirely because I added an acid to my solution. It didn't make a huge drop because it was a buffered solution, but I did add an acid and my pH went from the 4.74 from the original equation or problem to the 4.64. Okay. Last bit is what happens if we add a base. If I add a base to my solution, it's going to react with the acid that's in solution. Okay. So that's what the next problem is going to be. So again, here at the top, this was the original problem that we had, 50 mils, and we had 2 molar acetic acid and 2 molar acetate ions. Okay, remember again that the sodium is a spectator and he gets ignored. So when I look at this one, now I'm adding 6 molar sodium hydroxide to my original buffering solution. So I've got a weak acid and a conjugate base. I am adding a base, so it will react with the weak acid. Okay, so the first thing that I want to do, because I have a reaction between the sodium hydroxide and the weak acid, is I want to write a reaction equation. And so I've got sodium hydroxide, NaOH, and it's going to react with my weak acid, CH3COOH. And when that forms its products, I'm going to form sodium acetate, NaCH3COO, and water, H2O. This is an acid-base reaction. Remember, the split and switch, the sodium and the acetate combined, and then the hydroxide and the hydrogen combined to give me water. This is the second way to form a buffering solution. Okay. If you have a weak acid and you add a strong base to it, you will get that same salt that we looked at on the very second slide today. Okay, and this is the second way to form a buffering solution, is to simply neutralize half of your weak acid with a strong base. Again, we will cover that in more detail as we get into titrations. I'm going to ignore the sodium, and I'm just going to work with this acetate ion, CH3COO-. So what I need to do first, because we are working with bra charts, is I need to find the number of moles for all of the species in my equation. So these concentrations are going to be the same calculations we had in this last problem. I've got 2 milliliters of 6 molar sodium hydroxide. Remember that molarity moles over liters. I've got 6 is equal to X number of moles over 0.002. So my moles of base of the OH are 0.012 moles. I am ignoring the sodium and I'm just working with the hydroxide ions. When I look at the moles of my acid and the acetate ion, they are the same as they were in the previous problem. I have 0.100 moles of acid, 0.100 moles of the conjugate base. The sodium hydroxide is now the limiting reactant because, again, I have the 1:1:1 molar ratio. This is all going to get used up, and so I lose 0.012 moles of the hydroxide, and it reacts with 0.12 moles of the acid, and I form an additional 0.012 moles of my anion. So after the reaction is all concluded, sodium hydroxide is gone. I have no sodium hydroxide left. I have 0.088 moles of the acid remaining because I lost part of it that reacted with the base, and I have now formed 0.112 moles of my anion, the acetate anion here. I need to know a molarity, so I do what we did the last time. I had a 50 ml solution and I added 2 more milliliters to it. So I now have 52 mils, so 0.052 liters. This is going to give me a concentration of 1.69 molar. I divide this by 0.052 to get a concentration of 2.15 molar. Okay. The only thing that's different is the direction that those have gone. This is 0.169 molar of my weak acid, and this is 2.15 molar of the conjugate base. So taking those values and putting them into Henderson-Hasselbalch. Okay, Henderson-Hasselbalch again, pH is equal to the pKa of my weak acid plus the log of the anion concentration over the weak acid concentration. That looks terrible. So my pH is equal to 4.74 plus the log. My anion concentration in this case is 2.15. So 2.15 divided by the acid concentration of 1.69. When I plug that into my calculator, the pH of my new solution is 4.84. We give it the sniff test, see if it smells right. It does. I added a base, okay, to my buffering solution. So I added a base. Instinct should tell you, logic should tell you that the pH goes up. It did. It went from a 4.74 to 4.84, but because it was a buffered solution, it didn't make a tremendous jump. I know this video has been very long. I appreciate you sticking with me. We will continue to work on these types of problems as we move forward in class, but this is the beginning. We have to begin somewhere. If you have questions, please write those down in your notes so that you can ask the next time we are in class together. So I hope you have a good day, and I'll see you soon. Bye.